NENOMATICA, where mathematics meets YouTube excellence. Welcome to our math lesson on factoring algebraic expressions. Today, we'll learn how to factor out a common factor from a polynomial expression. Let's take a look at a specific example. Let's begin by finding the greatest common factor of all terms in this expression. First, we need to identify what is common to all three terms: 4x squared y cubed plus 2xy squared plus 6xy. Let's look at the coefficients first. We have 4, 2, and 6. The greatest common factor of these numbers is 2. Now for the variables, the first term has x squared, the second term has x to the power of 1, and the third term has x to the power of 1. So the common factor for x is x to the power of 1, or simply x. For y, we have y cubed, y squared, and y to the power of 1. So the common factor for y is y to the power of 1, or simply y. Combining these, we get that the greatest common factor is 2 times x times y, or 2xy. Now that we've identified the greatest common factor as 2xy, we can factor it out using the distributive property. Remember, the distributive property says that a times b plus a times c equals a times the quantity b plus c. So we'll rewrite each term by dividing it by the GCF, and then multiply the entire expression by the GCF. Let's simplify each part. For the first term, for x squared y cubed divided by 2x, y gives us 2xy squared. For the second term, 2xy squared divided by 2x, y gives us y. And for the third term, 6xy divided by 2x, y gives us 3. So our expression becomes 2x, y times the quantity 2x, y squared plus y plus 3. Let's review what we've done. We started with the expression 4x squared y cubed plus 2x, y squared plus 6xy. We identified that 2xy is the greatest common factor of all terms. Then we factored it out to get 2x, y times the quantity 2x, y squared plus y plus 3. So our final answer is 2x, y times the quantity 2x, y squared plus y plus 3. Let's verify our answer by expanding the factored expression. We'll distribute 2xy to each term inside the parentheses. 2xy times 2x, y squared, gives us 4x squared y cubed. 2xy times y gives us 2x y squared. And 2xy times 3 gives us 6xy. Adding these up, we get 4x squared y cubed plus 2x y squared plus 6xy, which matches our original expression. Perfect! So, in summary, we've shown how to factor out the greatest common factor from a polynomial expression. Thank you for watching. Remember, when factoring polynomials, always look for the greatest common factor first. This technique is the foundation for more complex factoring methods. Practice with different examples to build your skills. Happy studying! We want to factorize the expression 2ab plus 3b. When factoring an expression, we first look for the greatest common factor, or GCF, of all terms. In this case, we need to identify what common factor appears in both terms. In the expression 2ab plus 3b, we notice that b is a common factor in both terms. So we can factor out b from each term. So our answer is b times the quantity 2a plus 3. We can verify this is correct by distributing b back to each term in the parentheses. b times 2a gives us 2ab, and b times 3 gives us 3b. So we get 2ab plus 3b, which matches our original expression. Now, let's move on to a more complex example. Here we have 5a squared b cubed plus 10a squared b squared. Again, we need to find the greatest common factor of all terms. Let's analyze this expression carefully. In 5a squared b cubed plus 10a squared b squared, we can see that a squared appears in both terms, and b squared is also common to both terms. So, our common factor is 5a squared b squared. Wait, let me correct myself. The common factor is actually 5a squared b squared. So we have 5a squared b squared times the quantity b plus 2. Let me break down the factoring process more clearly. First, we identify what's common between 5a squared b cubed and 10a squared b squared. Both terms have a squared. For the b terms, both have at least b squared, with the first term having an extra b. For the numerical coefficients, 5 is common to both terms, as 10 equals 5 times 2. So the GCF is 5a squared b squared. Now, let's factorize by dividing both terms by the GCF. 5a squared b cubed divided by 5a squared b squared equals b, and 10a squared b squared divided by 5a squared b squared equals 2. So our factorized expression is 5a squared b squared times the quantity b plus 2. Let's move on to our third example. Here we have the expression for a squared times the quantity a plus b plus 8 a times the quantity a plus b. This is a bit different from our previous examples because we have a binomial expression, a plus b, appearing in both terms. In this case, the binomial a plus b is common to both terms. The other factors are 4, a squared, and 8a, so we can factor out the common binomial a plus b. Now, we need to see if the expression for a squared plus 8 can be simplified further. Notice that 4 is common to both terms. So we get a plus b times 4 times the quantity a plus 2. Let's summarize what we've learned about factoring algebraic expressions. When factoring, we look for the greatest common factor, which could be a single term like b in our first example, a product of terms like 5a squared b squared in our second example, or even a binomial expression like a plus b in our third example. Remember, factoring is essentially the reverse of distribution. We need to factorize the expression 2 times a minus b squared minus a minus b. Let's start by factoring out the common term a minus b. To do this, we need to identify what's common to all terms in our expression. We can rewrite the expression as a minus b times the expression inside the brackets. Inside the brackets, we have 2 times a minus b minus 1. Now, let's expand what's inside the brackets to simplify our expression further. We distribute the coefficient 2 to each term inside the parentheses. When we expand 2 times a minus b, we get 2a minus 2b, and then we subtract 1. So inside the brackets, we have 2a minus 2b minus 1. So our final factorized form is a minus b times 2a minus 2b minus 1. We have successfully factorized the original expression by identifying the common factor a minus b and using the distributive property to expand the terms inside the bracket. Let's move on to our second example. We need to factorize the expression 35, a cubed b minus 77, a squared b plus 14ab. Looking at all the terms in this expression, we can see that they all share a common factor of ab. Let's identify this common factor and use it to factorize the expression. In this example, we need to identify the greatest common factor among all terms. The process is to find the highest power of each variable that appears in every term and the greatest common divisor of the coefficients. Looking at our expression, we can see that each term contains ab, but the powers of a vary. The highest common power of a is a to the power of 1. For b, it's also power of 1. For the coefficients 35, 77, and 14, their greatest common divisor is 7. So our common factor is 7ab. So our final factorized form is 7ab times the expression 5, a squared minus 11a plus 2. We have successfully factorized the original expression by identifying the common factor 7ab. Let's move on to our third and final example. We need to factorize the expression 25a squared plus 30 a cubed minus 35, a to the power of 6. Looking at all the terms in this expression, we can see that they all share a common factor of a squared. Let's identify this common factor and use it to factorize the expression. In this example, we again need to identify the greatest common factor among all terms. The process is the same. Find the highest power of each variable that appears in every term and the greatest common divisor of the coefficients. Looking at our expression, we can see that each term contains with the lowest power being a squared. For the coefficients 25, 30, and 35, their greatest common divisor is 5. So our common factor is 5a squared. So our final factorized form is 5a squared times the expression 5 plus 6a minus 7a to the power of 4. We have successfully factorized the original expression by identifying the common factor 5a squared. Let's summarize what we've learned about factorization. First, we identify the greatest common factor among all terms in the expression. Then, we factor it out using the distributive property, which gives us our factorized form. Remember, factorization is essentially the reverse process of expansion. The factorized form can often simplify our algebraic expressions and make them easier to work with. We need to factor the expression 8x to the 4th power minus 4x cubed plus 10x squared. The The first step in factoring is to identify the greatest common factor of all terms in the expression. Let's look at each term. 8x to the fourth has a coefficient of 8 and an x with exponent 4. Negative 4x cubed has a coefficient of negative 4 and an x with exponent 3. 10x squared has a coefficient of 10 and an x with exponent 2. The common factor in all terms is x squared, since 2 is the smallest exponent of x in all terms. For the coefficients, we need to find the greatest common factor of 8, negative 4, and 10. The GCF of 8, 4, and 10 is 2. So the greatest common factor of all terms is 2x squared. Now, let's apply the common factor rule to factor our expression. The common factor rule states that m times a plus m times b equals m times the quantity a plus b, where m is our common factor. We can factor out 2x squared from each term to get 2x squared times the quantity 4x squared minus 2x plus 5. Let's verify our answer by multiplying. 2x squared times 4x squared gives us 8x to the fourth. 2x squared times negative 2x gives us negative 4x cubed. And 2x squared times 5 gives us 10x squared, which matches our original expression. Let's move on to our second example. We need to factor the expression x cubed, y squared plus 3x to the fourth power, y plus 5x squared y cubed. Let's analyze the terms to find the greatest common factor. For the first term, x cubed y squared, we have x with exponent 3 and y with exponent 2. For the second term, 3x to the fourth power, y, we have a coefficient of 3, x with exponent 4, and y with exponent 1. For the third term, 5x squared y cubed, we have a coefficient of 5, x with exponent 2, and y with exponent 3. Looking at the exponents of x, the smallest is 2 from the third term. For y, the smallest exponent is 1 from the second term. There is no common factor among the coefficients 1, 3, and 5 besides 1 itself. So the greatest common factor is x squared y. Now, let's apply the common factor rule to factor this expression. The common factor rule for 3 terms states that m times a plus m times b plus m times c equals m times the quantity a plus b plus c. We factor out x squared y from each term. This gives us x squared, y times the quantity x, y plus 3x squared plus 5y squared. If we multiply this back, we get our original expression. Let's tackle our third example. We need to factor the expression 3x to the sixth power minus 9x squared plus 3x. Again, let's analyze the terms to find the greatest common factor. For the first term, 3x to the sixth power, we have a coefficient of 3 and x with exponent 6. For the second term, negative 9x squared, we have a coefficient of negative 9 and x with exponent 2. For the third term, 3x, we have a coefficient of 3 and x with exponent 1. Looking at the exponents of x, the smallest is 1 from the third term. For the coefficients, we need to find the greatest common factor of 3, negative 9, and 3. The GCF of 3, 9, and 3 is 3. So the greatest common factor is 3x. Now, let's apply the common factor rule to factor this expression. We'll use the same common factor rule for 3 terms that we used in our previous example. We factor out 3x from each term. This gives us 3x times the quantity x to the fifth power minus 3x plus 1. We can verify this by multiplying back to get our original expression. Let's summarize what we've learned about factoring using the greatest common factor. In our examples, we factored 3 different expressions by finding and factoring out the greatest common factor. For the first example, we factored 8x to the fourth minus 4x cubed plus 10x squared as 2x squared times the quantity 4x squared minus 2x plus 5. For the second example, we factored x cubed y squared plus 3x to the fourth power, y plus 5x squared y cubed as x squared, y times the quantity x, y plus 3x squared plus 5y squared. For the third example, we factored 3x to the sixth power minus 9x squared plus 3x as 3x times the quantity x to the fifth power minus 3x plus 1. The key to factoring by GCF is to identify the common factor with the largest possible degree for each variable and the largest possible coefficient. For practice, try factoring more complex expressions with multiple variables. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.